Unit 2, Day 4, Algebra Proofs. Today we're going to be solving algebraic equations. However, we'll be solving it, writing it in a two-column proof format. In other words, we're going to show all our work, but then provide justification for every step. So some of the justification or properties that we can use to justify our work are as follows. The reflexive property, or the reflection property, says that r is equal to r or x is equal to x. So the same thing will occur on both sides. The symmetric property, or the switch property, says if a is equal to b, then you can read it as b is equal to a. The transitive property states if x equals y and y equals z, then you could cut out both of the y's and go straight to the meat, which would say x is equal to z. So the transitive property usually involves three terms or three variables. Now, the next four properties we've used over and over again in algebra, but you might have known they had a specific name or that you were actually using them. So anytime you add the same value to both sides of the equation, you're using the addition property of equality. Anytime you subtract one number from both sides of the equal sign, you're using the subtraction property of equality. Whenever you multiply the same number to both sides of the equal sign, you're using the multiplication property. And if ever you divide the same number from both sides of the equal sign, you're using the division property of equality. The substitution property of equality says if A is equal to B, then A may be replaced by B in any equation or expression. For example, if I say that A is equal to 2, then that means every A in that problem will be replaced or substituted with the number 2. Distributive property is familiar and should be familiar to you by name, because if you have a coefficient that's outside a set of parentheses with an operation taking place inside, your job is to take that coefficient or number outside and multiply everything inside by that number. So for example, if A times C plus B, then it's A times C plus A times B. So again, these are the justifications that we might use in the upcoming proofs. We don't have to use them all in every proof, and that's okay. But you still need to provide justification for each and every step. So in this first example of your first ever proof, I took the liberty upon myself to show all the steps for us, but we have to provide the justification for each step. So you're always going to be given something and asked to prove something else. So in this first example, it says we're given 3 times x plus 7 is equal to 4x plus 26. Our job is to prove that x is equal to negative 5. So the first statement on the left side of a two-column proof, statements go on the left, reasons go on the right, always, always, always. And the statements is basically your work section. And the reasons are your justifications for your work. So the first statement will always be your given information. So 3 times x plus 7 is equal to 4x plus 26. Now, the next step, you notice I no longer have parentheses, but in spite of it, it now reads 3x plus 21. What property was used in order for that to occur? It had to be the distributive property, because we took 3 times x and 3 times 7, so the distributive property was used at that point. Then we have to continue to isolate x. So the next step, you'll notice I have negative x plus 21 equals 26. So what happened to my 3x and my 4x in order to get negative x? I had to subtract 4x from 3x in order to get negative x. So I used the subtraction property on both sides of the equation. Now the equation is negative x plus 21 equals 26. So again, I'm still trying to isolate x. So I would have to, what next? Subtract 21 from both sides. And thus I would have negative x equals 5. So again, I use the subtraction property. But our goal is to prove that x is equal to negative 5, not negative x equals 5. So lurking in front of that x is technically negative 1. So I would have to divide both sides by negative 1 in order to completely isolate x. So that would cause me to use the division property of equality. Technically, when you get to step 4, negative x equals 5, you could choose to divide by negative 1 on both sides, or you could choose to multiply by negative 1 on both sides. So either property is valid justification for that step. Don't use both. So you could choose to divide by negative 1 or multiply by negative 1, whichever your heart desires, but don't use both. Now on this one, we are going to have to show all of the work together, and then I'll come back and we'll justify each step. So let me grab my handy dandy pen tool. And let's begin. So it says we're given 2x minus 18 equals 5x minus 39. We have to prove that x is equal to 7. So again, the first statement will always be what is given. 2x minus 18 equals 5x minus 39. The next thing I would do is take this 2x and subtract it from both sides. I like to always move the variables to the side of the larger variable. In this case, the larger variable is 5x, and it's on the right. So I need to move 2x to the right by subtracting. So that would give me negative 18 is equal to 3x minus 39. So now I would have to move my 39 to the left using addition to cancel it out on the right. And if I add 39 to negative 18, I would have positive 21 is equal to 3x. And then from this stage, I would know I would have to divide both sides by 3, and I would have 7 is equal to x. Now, I could leave it as 7 equals x, but I want it to read x equals 7, so I can simply switch it around. It's okay. It's logical. There's a property that backs me up. Watch and hold on. So now let's go back and justify all of our steps. So the first thing I did was I subtracted 2x from both sides of the equation. So that's how I ended up with 3x. So that was involving the subtraction property of equality. Then I had to add 39 to both sides of the equation, and thus I got 21 equals 3x. So I used the addition property of equality. Then I had to divide both sides by 3, so I used the division property of equality. And lastly, it first read 7 equals to x, but I wanted it to say x equals 7. So since I switched it around, I applied the symmetric property. So not too bad for your first proof. Again, you have to show work and just justify each step. Example 3, work it out by yourself and make sure you snap a photo of your work. Example 4, I'll work with you because, ooh, those scary fractions are in there. And I know we love them oh so much. But I'm going to work it with you to prove to you it's really harmless. So given that x plus 3 over 3 minus 5 equals negative 10, prove that x is equal to negative 18. So let me grab my handy dandy pen tool real quick. So again, here's my first statement is my given statement. X plus 3 over 3 minus 5 equals negative 10. So I have to first isolate that big, yucky looking fraction. So to isolate that piece, I would have to move this minus 5. How would I move minus 5? I would have to add it to both sides. So I would have x plus 3 over 3 equals negative 5. Because if I add 5 to negative 10, it would result in negative 5. Now, to interpret it, you could say x plus 3 over 3. Another way to look at it is x plus 3 divided by 3. So I need to get to x. I need x to be isolated, so I have to take care of this divided by 3 piece first. So to reverse a division when you're solving an equation, you have to apply multiplication. So I would have to multiply both sides by 3 in order to move that 3. So it would, once I multiply, I would be left with only x plus 3 on the left. And then I multiply with negative 5 on the right, and I would get negative 15. So now I'm at x plus 3 equals negative 15. And I know I still need to get x by itself by subtracting 3 to both sides. And when I subtract 3 from negative 15, I end up with negative 18. See, 4 steps. It was harmless. That fraction wasn't that scary. So let's go back and justify every step. So again, the first step is always the given step. Then what did I do? I added 5 to both sides, so I applied the addition property of equality. After I applied the addition property to remove that 3 from the denominator, I had to multiply both sides by 3. So I multiplied using the multiplication property of equality. And last but not least, I had to remove the 3 from both sides by applying the subtraction property of equality. So this concludes your tutorial or your instructional piece on the algebra proofs.